Good afternoon. My name is Robert Amos, and today I'll be presenting on my thesis topic, learning to follow an end-to-end deep learning approach. So first off, I'll just provide an overview for the rest of the presentation. I'm going to start off by providing some motivation for the end-to-end approach undertaken for the person following problem. I'm also going to outline the system architecture and design of the Casper platform, which is this robot over here. Then I'll give a brief overview of the deep learning methodologies that were utilized in the development of my end-to-end person following model, which was called DeepTrack, for which I'll then outline the model architecture of, as well as the data pre-processing augmentation techniques that were utilized to train the model, and also the training and evaluation of that model. I'll finish up with some conclusions and areas of future work. So what is end-to-end learning? In this context, it's referring to mapping of raw sensor data directly to actuator commands. And this methodology has been successfully applied to full-size cars for learning driving policies on road and off-road, just from directly from visual input. So in my thesis, I explore extending this extending this methodology to the person-following task, and hence developed my research question: can an effective driving policy for a ground-based platform learn an end-to-end representation to follow a person using visual inputs? So this is a system architecture for the platform. The ground station consists of a laptop with a gamepad as user input. At the heart of the Casper platform is the NVIDIA Jetson TX2 development board, for which the Wi-Fi module was reconfigured as a wireless access point to facilitate a 2.4 gigahertz Wi-Fi connection between the two systems. To control the system, the only sensor on the system is the stereo Z camera, and to drive the platform, an immersion box speed controller was implemented to drive a brushless DC motor as well as a steering servo. So this is a software architecture. Communication between these commands are sent to the Casper platform using UDP, and all drive-related computations performed on board the Casper platform. There's two modes of operation for the platform. Expert mode, which is used for developing the data set, so that enables manual control of the platform and the data logging module. And the second mode is the autonomous follow mode, which is where the DeepTrack module develops autonomous commands to drive the platform. I developed all these modules myself in Python 3, with the exception of the desk driver. So deep learning refers to the subset of machine learning algorithms that are focused around learning data representations, and more specifically applies to multi-layer neural networks. So there's two main building blocks of the modern neural network architecture, and that is the convolutional layer for multi-dimensional inputs, as well as the recurrent neural network for sequential inputs. I won't go into too much detail about these, but the convolutional layer is used for extracting spatial features, whereas the LSTM, or recurrent neural network, is used for extracting long-term dependencies, time-dependent features. The final concept that was utilized in the development of the DeepTrack module was multitask learning. So the intuition behind multitask learning is introducing subtasks to the model in order to steer the attention towards a desired goal. And I'll expand upon this in the next slide. So this is the model I developed for DeepTrack. So on the left-hand side of the model, there's four convolutional layers that extract spatial features from the input from the visual data from the camera. And on the right-hand side, I have an LSTM extracting temporal features from a feedback sequence of speed predictions. And those speed predictions are the last 10 predictions of the model. So down here I have the three output tasks: the speed prediction, the steering angle prediction, and the target detection task. The target detection task consists of predicting an X and Y coordinate, as well as the width and height of a unique target in each frame. And the intuition of this task is to help the model gain an insight into the relationship between the position of the target in the frame and the steering and speed prediction. Each of these outputs was regressed using the mean squared error loss function. So in order to create the data set for the model to learn from, the Casper platform was driven approximately 1.5 meters away from a lead person, and the lead person had this unique target attached to the back of them. In order to label all the large amount of bounding boxes that were required to train the target detection task, another object detection network was trained on the unique target. And this efficiently labeled all 25,000 images that I had in my data set. So another important aspect of training a deep neural network is to have equal label representation. So on this axis here, I have the number of samples that were in the data set, and on this axis here is the label that was applied to that data sample. So -1 is a normalized steering angle which has been normalized. Is a steering angle that's been normalized between the physical constraints of the platform. So -1 response is effectively a full hard left turn, and +1 is a hard right turn. As we can see, the zero angle here is overrepresented in the data set. So if we were to train the model directly on this data set, there would be an inherent bias towards driving straight, which is undesirable. So in order to address this issue, I introduced a few data augmentations, which can be seen here. So this image here is an example of a right turning sample from the data set. And then a flip has been applied here, along with a few opacity changes and a random shadow. And this gives the effect of creating a new sample of a left-turning image in the data set. So the model was trained on an NVIDIA GTX 1080 Ti GPU using standard backpropagation and the adaptive moment optimization framework. A learning rate of 0.001 was used and a batch size of 32. So the validation split for the data set was 10%, which means 10% of the entire data set was segmented out to validate the model accuracy after each training epoch. An epoch is defined as one pass through the training set. So the model took 50 epochs to train, which was about 10 hours, and we can see that the accuracy on the training data set is significantly higher than that of the accuracy on the validation set, signifying that the model was overfitting the training set quite significantly. This was to be expected due to the limited amount of data I was able to gather during the time frame. However, the best model from this was able to achieve the steering angle accuracy 83%, and that was at around the 33rd epoch. And correspondingly, the best speed prediction at that time was the 74%. So in order to determine what the network has learned, I dissected the convolutional layers. So we can see here that the model has learned to segment drivable from non-drivable terrain, and it's done this all by itself. We can also see that it has found the target in the frame. So moving further down the network, we can see higher order features have been abstracted by the network. In this case, we can see that the strongest activations here are coming from around the person of interest, and especially the target, indicating that this layer has learned a good representation of the person to be followed. So testing of this model was done in the same place where the data was collected to train the model. So we can see here, this clip here demonstrates one of the limitations of this approach, where the one poor bad prediction of speed leads to a flow-on effect of not being able to regather itself and ends up in a crash. However, there were some successes to this approach, such as this instance here, where the model is actually able to maintain a fairly good track of the person, as well as being able to recover from potentially driving off the path, as seen here. So in conclusion, I learned a lot about the convolutional neural networks and LCN networks that have been applied to end-to-end deep learning, end-to-end driving networks. I also learned a lot about the data processing, pre-processing and augmentation techniques that have been utilized throughout these models. And furthermore, for future work, I look to increase the size of the data set, as well as expand the testing to a series of other platforms. Thank you.
So we have time for questions. Any questions?
applying on your system?
So the model was predicting 10 hertz. It was a fixed time to predict at 10 hertz. However, that was just a limit that I'd set for the model for the model to run at. I didn't actually end up speed testing it, so that would be an area of future exploration to go faster.
I noticed you had the Z camera on there. Do you use the depth information?
So that was I intended to use that as an extra modality in training the network to begin with, but I just ran out of time to explore that.
So I noticed basically when you showed us that one of the deeper layers on your net, when you had somebody walking past the person that didn't actually even notice it.
No.
Why not?
I believe that was to do with the target detection task that was also steering the potential of the network. So the network would be so focused on that, detecting that target, that it would have effectively not noticed anyone else.
So the network remembers what it was doing before, so it's not just snapshots.
Yes, so the LSTM incorporates temporal, so time-related dependencies and examples. Think about that.
One more last question. Anybody?